Right, thanks for the very exciting introductions, and I'm really excited to be here to share some work I've been doing recently, not related to basins, not related to ice sheet, but try to look for can we find some link between geophysics and geochemistry isotopes. And you can see there's lots of people, lots of organization in the list. So I would like to acknowledge all the fascinating journey. I definitely learn a lot from this sort of interdisciplinary team here. So I guess the motivation we really try to think about that the Earth's evolution have near 4.5 billion years Earth's history, that we only have few tools can give us some ingredient for us to try to understand how the Earth actually evolves, the evolution of Earth through time. So basically, we have geochemistry and geophysics. When we think about geochemistry, we usually have some very interesting point information. So we actually have different like isotope ratios. With that, we can think about how things evolve through time. But bear in mind, because we don't have the spatial resolution of this isotope measurement, so we only have very locally sort of information to the things we want to understand. On the other hand side, we have geophysics, which thanks to the modern technology, we actually have more broader spatial coverage. But keep in mind, because geophysics only sensitive to basically give you a snapshot of modern day conditions. So we deal with different type of information. One type of information we have limited spatial information that can tell us some time information, time evolution. But the other hand side, we have good spatial coverage. So we don't really have the information about time. So most of the case, we just different domain looking for different part of the system, and we only sensitive certain part of the elephant in the room. The good news is I think in Australia and also all over the world have to start to investigate to get the spatial distribution of the isotope maps. So here show you example in near the North Australia and also North America. So everything here in the white dots is we have basically the isotope, the light isotope measurement. So we got enough data, we can start to generate some sort of patterns. Can use a point to make some contour map. I know it's probably a bit dangerous. And if you look more, look longer enough in the map, you probably might think about might have some spatial correlation with the things we see in the geophysics. But that's being said, we really need to be careful. If you look careful about the figure, you can see that the color signal are not really linear. And most of the case, we're really looking for the information we look at is not really the data itself. Actually, what we see actually based on the data that I see here. So the main talk I want to focus on is really try to think about can we think about if there are any systematic link between the isotope maps and the geophysical data? And if they have some sort of correlation, can we quantify this relationship or not? And if we can find some relationship, then things starting getting quite interesting because that will tell us some sort of information about either tectonic or the mineral system. And I guess the main motivation to talk to really try to hopefully using this platform to start a conversation, because we need basically three group of people. People deal with geochemistry, people deal with geophysics, and also people dealing with statistics. So hopefully we can find something, work together to look for some fun stuff. Okay, so before we jump to data, just go some like a geochemical 101, which if I say something wrong, please bear in mind, it's not really my field. So today we're gonna mainly look at the uranium and lead system. So basically the uranium perform decay into different light. So here you can think about have sort of bulk silicon earth in this green dots, and if nothing happens, we have sort of uranium 235 decay to 207, which have relatively short half-life. So basically, we can see a quite increased slope of the curve at the starting of the Earth. And then because the uranium-235 decay very quick, in the modern day, we don't have too many growth of lead-207. We mainly see a big growth of lead-206 due to the decay of uranium-238. So basically, that's if everything is homogeneous, we don't have cross and mantle, everything make our life so much easier, but probably they will boring. But actually, they have different type of the uranium reservoirs which cause different. This called uranium-238 and lead-204 ratio. So the way I think about the system, more like is think about the modern day Earth. We have this high radiogenic material in the crust, so we basically have higher uranium in the crust and sort of lower uranium in the mantle. So have high mu in the crust and low mu in the mantle. And if there's plate tectonic happens, think about the subductions, then we sort of mix this type of two system. So we start to generate some spatial distribution of this mu value. So we can measure the lead isotope, modern day lead isotope in the lab. So we can get the black dots, and then we can fit some like the curve, the lead isotope evolution model, give us a little bit understanding what's the age of the system, also the mu value in here. So basically, there's three information we're gonna look at. The first thing is the model age. We're gonna calculate using the lab ratio, and also the mu value we can also calculate using this evolution model. And the other thing is we call delta T, which is basically the tectonic age. We know that the actual age of the things we're gonna looking at, and this is the difference between the model age and the tectonic age. So things get a little bit complicated because we have different lead growth models. So here we mainly look at two models. One is called single stage model called MM model. So you can see basically the mu value is relatively constant, and we don't have too much variation for mu value. And the other model is two-stage model. We have relatively low mu value in the early stage of the Earth. And then at the later stage, we start to see the crust growth and then have higher mu value. So that's the thing we're going to look at the geochemical at the top point of view. And the other hand side, we have geophysics, which generates this beautiful red-blue blobs, which are sort of a combination of sort of different physical properties. For example, look like the mantle shear velocity. Basically, it tells us some information about what the temperature and the chemical composition in the modern day Earth. So keep in mind that have different physical properties, but we show the things in the modern day conditions. Okay, we have a little bit understanding about what system we're going to look at, and a little bit understanding what the geophysics, and then we're going to try to look at the data. So thanks for the quite hard work from the whole Australia. We now have near 1.6K points across whole Australia. That's the lead at the top. So at the beginning, I'm thinking probably we'll just do a contour map and then try to compare the information with the geophysics. Then I realized probably that doesn't really works because we see the data really don't distribute evenly, and then also they're likely to cluster together. So instead of generate a grid using the very sparse and irregular distribution data, I try to sample the geophysical information into the location we have the lead isotope. So we have, so basically left-hand side in the first column, we have this two-stage model, which have the model age, the mu value, and the delta T in here. And in the second column is this single-stage model. You can see there's basically looks similar, but there's some small variation in here. And in terms of geophysics, we're looking for both the crustal mantle properties. So here we have the shear wave velocity at 100 kilometer depth. So basically that's what you see in the modern day mantle conditions. And also have the lithosphere and sensory boundaries. So the first two gonna tell us the deep earth structures. And then we have some sort of crustal information with shear velocity as 20 kilometer and a manhole. And then we have some shallow structures get from gravity and magnetic. So basically we have sort of different type of physical properties and we cover different part of the Earth. So that idea, we try to see whether there's any correlation between these two data sets. So before we jump into too much detail about how we're gonna do this, we first gonna look at what's the data distribution to give us a little bit idea of what type of information we're dealing with. So here is the violin plot, basically just sort of rotate of the histogram. So here I sort of normalize the data, so everything have the same mean and standard deviation. So the first thing you can look at, basically, you can think about it, see the model age actually have sort of three major clusters in here. We don't see other things have this sort of major age-dependent information, but this model age do have, three big blobs. And if we go back to look at the tectonic age in the locations, we see the same thing. So basically, we see this sort of very old Western Australia, then sort of Proterozoic North Australia Gola Craton, and then we have relatively young stuff in the east. So basically, we have three different clusters in terms of the data we're going to look at. So the next thing, I just group the data based on the tectonic age. I have three age group, basically anything younger than 1 GA, 1 to 2.3 GA, and very old stuff, basically the sort of Yukon and the Pilbara Craton. So we can see both the model age and also the mean value actually sort of increase with the increase of the tectonic age. So we see this sort of different distribution compared to other values. And if you look at the geophysics, you also see the similar stuff in the lithospheric mantle. If you look at the shear velocity in the 100 kilometer depth, also the lithospheric sensory boundary, we do see this sort of increase of velocity or increase of the thickness of lithosphere through time. And we don't see similar information in the crust. I guess probably due to this weird things happen in Proterozoic, but we will not talk about this stuff in today's talk. Okay, so now we have some idea about what the data distribution looks like, then we try to build the connections. So how we do that? So the way to think about is we actually can use sort of data-driven approach to tell us what the relationship between these two different variables. I guess the hypothesis is if we see there's a correlation of the geophysics data and the geochemistry, then we can try to use the geophysics to mimic the pattern we see in the geochemistry. So here I'm using sort of a random forest is based on a sort of ensemble tree-based regression tree. So basically in each tree, I use a subsample of the geophysical information, try to fit the pattern we see in the geochemistry. I think the good thing in these techniques, we can actually using this basically the mean decrease impurity to give us a matrix to see, if these two variables has a relationship, then which variable is more important or driven this relationship. So we also can look at the permutation importance, but we am not showing here. So basically, we're gonna try to use random forest, the metric, the importance by the random forest as a tool to tell us whether the geophysics and geochemistry have a relationship, and if they have a relationship, which type of information really driven this type of relationship. Okay, that's basically the introductions, and then we can look the data. So here is the metrics in the whole Australia. The first row is a two-stage model, and the second row is a single-stage model. So if you look the first thing is the model age. You can see the mantle condition really sort of pop up in terms of the importance compared to the the other information we see in the crust. So we see the velocity at 100 kilometer depth and the lithosphere thickness really shows driven this relationship. Similar things we also see that happens in the delta T here. And in terms of mu value, they have, the things have something represent the mantle, also something represent the crust. If you think about, go back to the, think about the lead isotope, lead evolution curve, actually they make sense. That's sort of one thing sensitive to changing at the mantle, also sort of a mix in the crust. We'll go back to the point later of this talk. So basically we see the mantle sort of correlate with model age and delta T and mu, and the correlation is relatively strong here. And remember, we have 3 different age classes we see before, so we're going to zoom in each age class to see if there are internal variations in here as well. So the first thing we're going to look at is the younger stuff in the East Coast. And again, we do see this, strongly mantle-derived relationship in here. And also we see some sort of information in the crust as well. We see the manhole is quite important. Think about to looking for the mu value in here. And actually, there's a publication from Dave Houston that looking for what actually the geological meaning in this area. So it turned out that they think about the potentially there's two continents, Proto-Australia and Proto-Pacific boundary, and there's sort of there's subduction due to the Proto-Pacific in the east and to the west, called this like the spatial distribution of both variation of mu value and delta T. So which sort of makes sense. We do see this, the mantle conditions and also the thickness of the crust really driven the patterns we see in the geochemical data. So I guess probably that's the positive things that we can start to try to think about link them things together. And the other thing, the next slide is probably more interesting. We're gonna look for the middle part in North Australia and Angola. And if you look the MM model with a single stage model, we do see this quite strong, the LAB, which really show up in the mu patterns we see in here. And also, if you look the 2-stage models that in here we have this, the manhole, so basically the boogie gravity, so the gravity sort of sensitive to the long waves and boogie sensitive to the manhole, also some sort of crustal structure as well. And then there's really sort of fit well with these things we see visually, that we see there's a sort of correlation with the mu value, mu pattern we see in here with the boundary of the lithosphere, also the boogie gravity. And also we have looking for have the new model from GA with the MT. I haven't put in the framework. I will try to do a later stage. So and then we think about what's the implication in there. We probably have this sort of rifting happens in the margin of the the cratonic lithosphere, which driven the pattern we see a gradient of the gravity, a gradient of the isotopes, and this big transition of the lithosphere. And also the interesting part, also there are lots of mineral deposits in here. So the last thing we'll look at is the relatively older stuff in WA, which we do see there's also the mantle conditions also in here, but we see more information come up from the crust. So we tend to see probably there's sort of crust control about the things we see today, which probably makes sense because everything there is sort of quite old. So probably more things we see is driven by the crustal information. Okay, cool. A short summary that we try to use using basically random forest help us to build a matrix to try to link these two different property together. And we do see there's a correlation in there, at least in large scales, is correlated with broader lithosphere architectures. And probably we see some, that indicate there's some process that happens in the lithosphere, either due to subductions or there's some like evolution of the the margin of the cratonic lithosphere. And the other thing we see in the small scale, there's seems to be more complicated and correlated to the crustal structures, and probably need a little bit more work to try to understand what actually that means. I guess I'm feeling probably they'll link to some thermal evolution in the crust, but we haven't dig into much detail yet. So yeah, so that's all from me. So thanks for your time. I'm happy to take questions if you have.